this sort of is associated with the notion of value functions for MPP. So imagine we are initiating the system or the environment as an initial state as thought, and the agent will be rolling out a sequence of actions following the policy. And along this trajectory, the agent will also be collecting rewards along the way. If we add all together these rewards with a discount factor for future rewards by a factor of gamma, so that the more immediate rewards will be carrying more value to the agent, we are essentially arriving at this value function where the argument of the value is the initial state we are figuring for the average. So this discount factor gamma is a very important quantity. So the setting we are describing here is essentially this infinite horizon discounted setting. And because the reward function is bounded between 0 to 1, if you think of this as a geometric sequence, you can immediately see roughly after the time step 1 over 1 minus gamma, the reward that is collected at the time essentially carries minimum bearing to the agent. Therefore, we'll be usually thinking about this parameter, this 1 over 1 minus gamma, as some sort of effective horizon. That is usually sometimes very convenient if you want to translate results that you have for the infinite horizon setting to the finite horizon setting. You essentially only need to replace the effective horizon by the finite horizon. All right. Another important function is the Q function. So the Q function is very similar to the value function, except that instead of taking the first policy following the instead of taking the first action A naught following the policy time, now I'm going to also fix the first action to be any element from my action space, and then rolling out the rest of the action following the policy. So the Q function is a two-dimensional function over the product of the the state space and the action space, and often it plays a very important role in finding the optimal policy. All right. So with this sort of notion, the value function in hand, we can sort of formally say what is our goal for this MDP problem. This is essentially just finding the optimal policy that maximizes the value function. If the environment is known, so we know exactly the probability transition kernel and the reward function, this is a problem that is well solved by the literature of dynamic programming and optimal control, where we can simply run the Bellman's optimality equation. However, in reinforcement learning, often the environment is unknown, and we need to be able to sort of simultaneously either estimate the environment explicitly or implicitly while figuring out the optimal policy. In this talk, we'll be using the notation star to indicate optimal functions. So every time you see a star on the value function on the policy, they're associated with the optimal quantity for the given activity. All right. So as I said earlier, if you know the model, you can solve the problem through the Bellman's optimality principle. This turns out to also be serving a very important role in the design of reinforcement learning algorithms. So just let us review this very well-known Bellman operator. This is a Bellman operator that applies to any two-dimensional function that's like a Q function, and also will be another Q function, but sort of an improved version of pump, based on one-step look ahead. So imagine you are at the current function, you'll be updating the specific element of your Q function based on the immediate reward, and so the next day's best value through bootstrapping. And importantly, this Bellman's operator satisfies two nice properties, where the optimal Q function, which is what we are interested in finding, turns out to be the unique fixed point of the Bellman operator. So if you can solve this fixed point equation, you solve the dynamic programming problem. We also know this Bellman's operator is a gamma contraction. with respect to the L infinity now. And this is important property so that we can devise efficient algorithms to solve this Bellman's equation, such as policy iteration, value iteration algorithms. If we know notice that in this Bellman operator, we are actually assuming we know the transition kernels. So if we know the model, we can directly use this classical approach. But in reinforcement learning, typically the model will not be unknown, so we cannot directly solve this Bellman operator, but rather try to solve it approximately through interactions with samples collected from the environment. All right. So with this sort of basic background knowledge in mind, now let's go ahead and evaluate some of the IL algorithms. The first algorithm we'll be looking at is this Q-learning algorithm. Particularly, we want to understand its sample efficiency and examine whether it is min-max optimal. To do so, I need to figure out a way to know where I'm generating my samples. In this talk, we'll be focusing on the simple setting where I assume I have a generating model. And this is a model where essentially it allows you to query any given station action pair. And for that given state action pair, the generating model will tell you what the next state will be. So this is sort of simpler model than practically in the sense I can essentially probe any state action pair I want, so I don't need to face the issue of exploration, but just focus on exploitation itself and see how hard it is to actually solve the exploitation aspect of our problem alone. And this is still sort of a challenging problem from a statistical point of view to understand the sample, how many samples we need, both from a necessity point of view and from a sufficiency point of view to solve the IL problem. Right. So from sort of a necessary point of view, we actually know from this paper by Ada back in 2013 that they show if you want to reach entry-wise error to the level of epsilon for estimating the optimal Q function, you need at least the number of samples on the order of SA divided by 1 over gamma to the third order times epsilon squared. All right. So this is the sample complexity that you need no matter what algorithm you use. No algorithm can succeed if they have an amount of sample below this order. This is sort of an interesting result because if you just ignore for a moment the dependencies with the discount factor or the accuracy level, this is roughly saying the amount of sample you need is only on the order S times A, which is roughly speaking the size of your Q function. And this is actually much, much smaller than the dimension of your probability transition kernel, which has a dimension of S squared times A. So this may be indicating we can solve the IL problem, we can solve this control problem without accurately estimating the model itself, which is actually very, very interesting. So the question is, can we actually achieve this bound? Or in particularly, we'll be looking at can Q-learning actually achieve this bound? So what is Q-learning? As I mentioned before, the optimal Q function can be found by solving the Bellman equation. However, because we don't have the model exactly, we cannot directly solve the Bellman equation. Rather, we can use samples to approximately solve this. And naturally, this leads to this approach of stochastic approximation of Robinson and Monroe. And Watkins and Dayan essentially apply a stochastic approximation to solve this and arrive at the Q-learning algorithm. So specifically, instead of having the exact knowledge of the Bellman operator, we're going to have some sort of data-driven approximation of it at each iteration. And we're going to sort of update our Q function estimate by a weighted combination of the previous Q function and also the new information we are collecting from the current stochastic realization of the Bellman operator. And in the generative setting, we'll be allowing ourselves to probe all the state action pairs. And yes, is there a question?
Is
there a question?
Mr. Vishwajit Shahu, can you please mute your mic? I think there is some noise coming.
Alright, so if we look at the way we are designing this Q function and compare from the previous population level bounded operator structure, so this TT operation essentially is a data-driven quantity that we replace the expectation over the next possible state simply by the max from the next state, right? Because we are only drawing one sample rather than evaluating the average over the transition. Alright, so you can see Q-learning is actually a very simple, intuitive algorithm and has been very popular sort of the workhorse of reinforcement learning over the years. What do we know about the sample efficiency of Q-learning? There has been a lot of prior work to try to understand Q-learning, as you can imagine, because this is a sort of very fundamental algorithm. If you look at the prior art, there's the most state-of-the-art results from the last 2 years of the paper by Wainwright and Chen et al., where they essentially established the sample complexity on the order of SA divided by 1 minus gamma to the 5th order times epsilon squared. And if you benchmark this sort of prior best upper bound with the minimax lower bound we just mentioned, you see it is almost optimal with respect to all the parameters, except the dependency with the effective horizon, where the upper bound has a dependency of 5th order, 5th order, and the lower bound has a dependency of 3rd order. Alright, so this is kind of a curious gap, right? That's something we want to understand. Does this mean Q-learning is indeed non-optimal from this minimax perspective? Or is there an analysis artifact that it's just that people didn't analyze the algorithm tight enough? So we were driven by this question, and we tried to also look at the sample complexity of Q-learning. And indeed, it turns out that this upper bound analysis can be sharpened a little bit. And what we've seen is that we can essentially get epsilon accuracy as long as the sample set is on the order SA divided by 1 minus gamma to the 4th order times epsilon squared. So this improves the dependency with the effective horizon from the 5th order to the 4th order. And this algorithm sort of works when you choose just learning rate sort of effectively within this range that is shown below. So roughly speaking, this sort of accommodates two popular choices. One is a constant step size, and the other is the so-called rescaled linear rate, where you see on the right-hand side, this is it looks like something like 1 over t, but you actually also add a bias term, which is important for the success of the algorithm. All right. So the question is, now we're at the 4th order dependency, but still we are 1 order away from the minimax lower bound. Can we actually get to the minimax lower bound? And there's empirically, it seems actually not possible. If you just look at a very toy example at the left, where you only have 2 states, and at state 1, you essentially have 2 copies of the same actions, the red one and the black one, where they have exactly the same consequences. And even for this very small toy example, we see that Q-learning actually indeed has a scaling, the sample complexity has a scaling with respect to the effective horizon on the 4th order. So this seems to be suggesting Q-learning is actually not optimal. Can we make this rigorous? Just by sort of formalizing the intuition from the toy example. And turns out we can. And this gives us another lower bound, which is an algorithm dependent lower bound, because this is a lower bound tailored to the analysis of Q-learning. And we show there exists an MDP where Q-learning need at least a number of samples that is on the order as A divided by 1 minus gamma to the 4th times epsilon squared. And this holds both for the constant and rescale linear learning rate as well. So on the board, I'm showing you the example we analyzed for the serum, which is a slightly more complicated model than the numerical example I showed earlier, where we introduced a couple more redundant states just to make the analysis easier. All right. So if you put these two things together, now we have to pinpoint a matching lower and upper bounds for the sample complexity of Q-learning, where the dependency with the effective horizon is on the 4th order. And this actually sort of shows Q-learning has a proven gap from the minimax lower bound, which is on the 3rd order. So this suggests Q-learning is actually not minimax optimal, which is somewhat surprising because we actually know if you take a model-based approach, model-based approach is actually minimax optimal that can achieve the minimax lower bound. But our model-free algorithm, the Q-learning algorithm, is actually not minimax optimal. Why is this the case? Empirically, people have been seeing this phenomenon already back in the 90s, actually. And this is often credited as the issue of overestimation for Q functions. In the sense, if you look at the operator in the Bellman operator, we are doing this sort of taking maximization over some expected quantity. And this often tends to be overestimated, meaning it has a high positive bias when we are replacing the expectation using some sort of empirical estimates. Often this actually gets worse when we have a large number of actions. And it's on the right, I'm showing an empirical figure from the double Q-learning paper by DeepMind, where indeed they see that the bias that you are getting, basically are these red bars, are getting worse as you have more and more number of actions. And empirically, this has motivated a lot of sort of fix for this problem. For example, this double Q-learning algorithm proposed by Hassel essentially tries to fix this issue by introducing another Q estimate sequence. And you can see this blue bar that is essentially the fixed outcome of this double Q-learning algorithm. There are also other fixes that are provable. For example, if you introduce sort of variance reduction ideas into Q-learning, you can also make it to be provably minimax optimal. But the vanilla Q-learning algorithm, as we've seen, is actually not minimax optimal. All right. So now I finished my discussion about the Q-learning algorithm. I want to just pause briefly to see if there's any questions I can answer right now.
Ma'am, there are no questions in the chat as of now.
All right, so let me maybe continue and we can delay all the questions to the end.
Yes.
So the next part will be shifting gears a little bit and try to understand another approach to reinforcement learning using policy optimization. This is more, rather than from a statistical perspective, this will be more on some of the optimization aspect. Trying to understand the non-convex optimization problems induced by reinforcement learning tasks. Roughly speaking, putting everything under the umbrella of optimization, policy optimization tries to solve optimization problem where the objective function is essentially the value function, parameterized by some policy, which are so often parameterized by some other parameters theta that is sort of amenable for optimization. This is popular and sort of beneficial for several reasons. First, because it actually tries to directly optimize the policy, which is often the target of interest This is the thing that we actually execute as an agent, which is in contrast to the value-based case where after you get the value function, you still need to sort of do a gradification of the Q function in order to derive the policy. And this also allows us to take into account sort of harness the power of the very flexible parameterization of the policies such as the deep neural networks to be embedded very easily into this optimization framework. And we can sort of work with hybrid problems very conveniently, where the action space may be taking both continuous variables and discrete variables. That is very conveniently can be done in this policy optimization framework. Nonetheless, there's a lot of theoretical challenges associated with understanding the global convergence of policy gradient methods. There has been very little understanding until recently, mostly because this type of non-concave maximization problems are known to be susceptible to bad local maximas or saddle points if we just draw intuitions from classical wisdoms in optimization theory. The recent findings has been really motivated by the realization that this type of problem we are looking at is not any arbitrary problem, but problems induced by the structure of the underlying reinforcement learning problem, either MVP or some other control problem. And if we leverage the problem structures, maybe we can say much more and a lot more about the performance of this algorithm. So this is essentially what we are going to take into this talk, and we'll try to understand finite convergence rates of some popular heuristics like policy gradient methods. And if time permitting, I'll also talk briefly about some other finite convergent, about other fast convergent algorithms for finding policies with desirable structural properties through the use of regularization. All right, so let me introduce this policy gradient method. As I mentioned, the goal is to maximize the values, but the value is defined in a per state manner. So the first thing we are going to do is crash all these numbers into a single scalar function that we call our objective function. So to do so, we'll be introducing this initial state distribution rho and averaging the value function over this initial state distribution. And our objective function will be parameterized similarly now by this distribution rho that you are taking. The policy we're interested in optimizing is a distribution over the action space when we fix the state. So this is a constraint problem. To remove the constraint, a very popular parameterization people will take is the so-called softmax parameterization, which is essentially taking the value of the policies as through this exponential map. So we're mapping the policies to the parameters theta, which are unconstrained numbers over the real. So with this allows us to rewrite this problem into an unconstrained maximization problem over the parameter space theta. And now we essentially arrive at a very convenient form for optimization. And what this policy gradient method starts is essentially optimizing the parameter theta along the gradient ascent directions of the value function using some learning rate eta. Right? So this is very simple sort of first optimization method that will come to mind. We'll be mostly studying this population version, meaning we'll be thinking these expectations embedded in the value function can be evaluated perfectly, assuming we have the perfect model information, but just focusing on the optimization perspective for them. So if we assume we have exact gradient evaluations, how can we guarantee the convergence of this policy gradient method? There has been a very nice paper by Agavo et al. in 2019, where they show indeed the softmax policy gradient converge asymptotically to the global optimal policy. However, they do not tell us how fast the algorithm converges. Another follow-up paper by Mayo showed that the algorithm actually converges at the rate of 1 over epsilon, the sublinear rate, with a pre-constant that can depend on all the salient parameters. However, they haven't told us the dependencies in this pre-constant. They didn't tell us explicitly how these dependencies actually look like. So this means we still don't know exactly the rate of this PG method. It is not clear whether this rate is indeed fast enough or this can be sometimes very slow. And on the flip side, we actually delivered a negative message showing you can actually find MDP where if you run the softmax PG to drive it within a constant error, it already can take you a sort of super exponential number of iterations on the order as to the truth order to the order of effective horizon. Okay. So this means for some type of problems, the algorithm can converge extremely slowly and become problematic, especially for problems with large state space and long effective horizon. I'm not going to show you what the example we constructed look like, but essentially that look like a chain MDP, where the convergence time essentially grows geometrically over the chain. So in order for all the states to find the optimal action, and when you add up the sort of convergence time over the chain, that gives you this super exponential time convergence result. All right. So this seems to be suggesting, although PG can converge asymptotically, but in some instances it can converge very slowly, even exponentially slow. And this is like driving a pumpkin cart on, say, a New York street at the busy rush hour, where you could imagine this pumpkin cart eventually will take you to your destination, but it can be painfully slow. And at this point, maybe it will save you a lot of better time by taking the subway, right? If you can find an alternative approach that can converge much faster. So we want to boost up the convergence of PG. So how do we do this? The first booster we'll be looking at is this natural policy gradient approach, where instead of updating our parameter along the direction gradient, we'll actually look at precondition gradient, where we're going to precondition the gradient by the inverse of the Fisher information matrix. This is constructed based on information of the parameterization. So roughly speaking, this approach allows us to update our policy, sort of stabilize our update of the policy to be insensitive to the different ways of parameterization. Another booster is the so-called entropy regularization, to specifically to enhance the exploration of the policy in use. We want to be able to promote the stochastic of the policy in use by sort of in order to avoid it to prematurely settle on some suboptimal policy. So to do so, one way to think about this is we are going to adjust the reward function at each step. In the sense, besides the common reward term we have, we're going to also add in another term that is proportional to the Shannon entropy of the policy, so that policies with a higher stochasticity will be favored from the value function. With this adjustment of the value function, we essentially arrive at optimization problem that our goal is now to optimize this regularized value function instead. Alright, so how does this two tricks help us? Now here I'm showing you a toy example where we are looking at a bandit example with 3 arms that has 3 different rewards. So the bandit is a toy aisle problem where you only have a single state. And we can already see on the left corner, if you run policy gradient, it actually converges to the optimal policy through this sort of indirect path. So all these blue lines are showing sort of the gradient flows, or the natural gradient flows, pointing towards optimal policy. And here you see if you use natural policy gradient on the right panel, you actually converge to the optimal policy following a much more direct path, indicating the convergence is much faster. Similarly, as you increase the amount of regularization, you can see both for both policy gradient and natural policy gradient, the gradient flows becomes sort of more smooth and having a more direct path towards the optimal policy. Even though, as a small warning, we are solving a slightly different problem due to the change of amount of regularization. So the optimal point is also being shifted as we are adding in more regularization. Indeed, these two ideas has been very popular in practical problems where this very popular algorithm called TRPO, which is used to train model IO agents, it's nothing but natural policy gradient coupled with a more careful way to set the the learning rate through line search. Then we also see in some of the papers by Google and DeepMind, they see that adding entropy regularization indeed helps exploration and is very useful for accelerating the convergence of the algorithm. So from a theory perspective, we really want to justify this phenomenon. Can we justify the efficacy of this entropy regularized natural policy gradient descent? Not descent, natural policy gradient method. Now again, if you look at just the tabular setting, you can actually rewrite the update rule directly over the policy space, where you see the policy is essentially being updated as this multiplicative combination between your current policy and the soft gradient version of the value function of your current policy. And here, the learning rate is within the interval from 0 to 1 minus gamma divided by tau. So if you add up the exponents on both terms, they add up to 1. And this update rule is actually invariant with respect to the choice of the initial state rho, even though when we first sort of write down the optimization problem, we introduced it. And if you take the largest possible learning rate, 1 minus gamma divided by tau, you see you are essentially dropping the first term, but only keeping the second term, where you are updating the policy as an exponential map based on the value of the current policy. And this is essentially a soft version of the classical policy information that takes exact greedy operations. Here, we are taking a soft one through the exponential map. So already you see a lot of connection of this with classical algorithms. So assuming we have perfect policy evaluation, we actually were able to establish this entropy regularized MPG actually converge linearly to find the optimal solution of the problem. Let me interpret this result a little bit. You don't need to read all the quantities here. But the key message is, if you want to reach epsilon accuracy, the iteration complexity, if you're taking a general step size, is roughly speaking on the order of 1 over epsilon tau times log 1 over epsilon. Where if you fix the learning rate eta and letting the entropy regularization tau is larger, your iteration complexity actually becomes smaller, indicating a higher amount of entropy regularization helps to accelerate the convergence. On the other end, if you look at the special case of soft policy iteration complexity essentially reduced back to the effective horizon, which actually matches with the iteration complexity of policy iteration in the classical literature. More importantly, we see we actually are guaranteeing a global linear convergence at a convergence rate that is independent with the size of the state space and the action space, which is in sharp contrast to the potentially super exponential convergence time that needed by the original vanilla policy gradient method. Here we are achieving a dimension-free linear rate of convergence. Now, as we have introduced two types of boosters, let's just look at a little bit, do a little bit of ablation study to see the consequences P1, the booster. So if we compare this performance guarantee with the entropy regularized PGMSO, where we are not using natural gradient. So in this paper by Mayo, they also showed this linear rate of convergence result for entropy regularized PG. But nonetheless, this result again has this unspecified parameters that can grow exponential with respect to the size of the state space and effective horizon. On the other end, we are guaranteeing the linear convergence of entropy regularized NPG. With regularization, we actually achieve a linear rate of convergence on the other log 1 over S3. So although this should be taken with a grain of salt, because by adding regularization, we are solving a slightly different problem. So we're not finding exactly the same solution. But from the optimization perspective, this again corroborates the message that entropy regularization indeed helps to enable fast convergence. And there's so before I move forward, I just mention one thing sort of very interesting because it helps to tie this classical dynamic programming with this more modern policy optimization algorithm with entropy regularization. So it turned out for our analysis of this entropy regularized problem, a key operator pop up, which can be thought of as a soft version of the Bellman operator, where we essentially modify, especially the second term, based on by adding in the impact of the entropy regularization. And it turns out that this soft Bellman operator also inherits this two important property of Bellman's operator, where this regularized Q function becomes a fixed point of this soft Bellman operator. And moreover, it also satisfies this gamma contraction property. So with this soft Bellman operator in place, immediately we can see we can already analyze our algorithm for the special case of soft policy iteration, where by directly mimicking the analysis for the classical policy iteration algorithm, where we are doing this dance between the policy and the evaluated Q function through the policy evaluation and gradification. And we can basically directly copy the fruit for the soft policy iteration algorithm by only changing the greedy step as a soft greedy step. For the more general case, for the general step size, the analysis needs to be a little bit more complicated, where we actually need to build a linear system and carefully control the contraction of the algorithm through analyzing the spectral property of the linear system. But the proof is actually also sort of very short and sort of elementary, I would say suitable for reading even at the undergraduate level. So if you're interested, you can read our paper to see the more general case. So because of time, I'm going to move faster, but just to mention two things, just maybe on a high level, this regularization idea beyond just the entropy regularization. So it turns out that if you, this regularization is sort of this more general tool that we can also use to promote structural properties of the policy. In the sense, if you think about, for example, cost-sensitive settings, if different actions may bearing different values to you, then maybe you want to be preferring certain actions during the learning. And so regularization can be used as a scheme to add in this sort of prior assumptions and the preferences about the learning policy into our framework. And this sort of calls to this more general form of regularize our problem, where instead of injecting this entropy regularization, you can essentially take a favorite regularization function and bring them into this regularized loss function and use policy optimization to optimize this regularized loss function. This again is a benefit of using policy optimization for solving IO, because it's giving all this flexible way to dump your requirements into the objective function. Without getting into the details, it turns out that we can sort of harness the things we learned by analyzing entropy regularized MPG to develop this more general version or more general algorithm that can work with an arbitrary regularization function that we can come up with algorithm called generalized policy mirror descent. And this algorithm has a similar sort of linear rate of convergence result as the entropy regularized MPG method. And we show that through numerical examples for some type of other regularization function, this generalized PMD algorithm achieves a faster convergence than the previous algorithm developed in the literature. So because of time, I'm not going to get into details about this more general framework, but just want to hint you on the high-level message where we can think of framing a more general family of regularized problems beyond just the use of entropy regularization. All right, so to put everything together, in this talk, we've sort of discussed two types of approaches. One is the value-based approach, the other is the policy-based approach. And I try to understand both their sample use and the computation use through a sort of non-asymptotic lens. And we hope that through this analysis, this helps to shed more light to why these algorithms are successful and sometimes sort of unsuccessful in practice. And hopefully some of the theoretical insights can be used to devise better algorithms that people can use in practice. There are a lot of interesting future directions. The talk has been primarily focused on the tabular setting. Understanding the performance in the function approximation regime is a very, very important and critical direction. There are also other variants of reinforcement learning problems agents in place called multi-agent trial. So with this, I want to conclude the talk. These are some of the relevant papers pertaining to today's talk. You can find them on my website. If you are interested, I want to also mention we actually are offering a tutorial on reinforcement learning, which covers actually some of the content you hear about today. As the tutorial is actually upcoming this weekend at ICAST. So if you are attending ICAST, I invite you to attend our tutorial. With this, I will conclude. Thank you so much for your attention and for the invitation again. I'll be happy with any questions you may have.
Thank you so much, ma'am, for the talk. So we can now open the floor for questions. If anyone has any questions, you can feel free to unmute yourself and ask.
I guess it's a lot of contents in 1 hour. The actor runs this policy gradient update, which is what I talked about in the second half. And the critiques that update the value function is kind of the Q-learning type of algorithm, the value-based update. So you can actually also analyze final time convergence or actor critique, leveraging some of the results we talked about. I don't have results myself on actor critique, but there is also a lot of papers that try to analyze convergence of finite time guarantees for active critique algorithms. So they sort of sit in between the value-based and the policy-based algorithm.
One more question from my side. So as I understand in supervised learning, we have something called the loss function which guides us towards the direction of convergence. So when the algorithm converge. So is the value function which you described in the lecture analogous to the loss function?
Yeah, except you are maximizing them, right? Sometimes people want to make it similar to the standard optimization where people want to look at minimization. Instead of doing the reward, they talk about cost. So every time you make an action, you incur a cost. And then you will have a cost function. And then you minimize the cost function. But that's essentially the objective that you have.
Thank you, ma'am. So if you have no more questions, I ask Ratul to provide the concluding remark.
Yeah. Hello. Sorry. Okay. So I hope have a good